Let's start by creating a geometry node. Let's name it ink and dive inside the node. You can either double click on the node or press enter. And as an emitter, I'm going to use a simple sphere. So press tab and look for the sphere node. Now what I'm going to do is change the diameter of this sphere to 1 meter. So change the radius to 0.5, 0.5 and 0.5 in X, Y, and Z. And since we're using a uniform scale of 1, this value, a diameter of 0.5 scaled at 1, would yield a 1 meter diameter sphere. Now consider that this is a huge sphere in terms of what we're photographing or rendering. But in the end, I will scale down the simulation. Right now, I just want to get nice shapes, and the scale can be easily handled later. So for now, let's make sure to change the primitive type to polygon. Let's also increase the frequency to 40, just so we have a very smooth surface. Now, before I continue, let me mention 3 things that we will need for the simulation. So we can create a sticky note here. So first of all, we're going to need the density. We will also need the velocity. So in terms of the volume, this would be the vel. And when you're talking about particles, it's usually the V attribute. And finally, we will need the color or the CD attribute. So we will need to create 3 different volumes representing these attributes. This is what we're going to feed into the simulation. So first of all, let's take care of creating some points that later we can rasterize. So I'm going to press tab and look for the points from volume node connected below the sphere. And what this node is going to do is create a number of points scattered evenly on the sphere, almost as a grid of points. So let's increase the amount of points that we have here. I will reduce the point separation. Let's start with 0.05, just so we have a little bit more points here. And now let's create a density attribute. And you can do this in many ways. I prefer to do it through a point wrangler just because it's more flexible to change afterwards. Probably you want to link an attribute to another, or probably you want to multiply or even animate the attribute. And this is relatively easy to do with a point wrangler. So let's add a point wrangler just below our points from volume node. Let's change the color of this wrangler and also change its name to set density. So to create the attribute, we can define, first of all, what type of value this attribute is. It could be a float, a vector, a string. In this case, the density is a float value. So you can type f at and then the name of the attribute that you want to create, in this case, density. Finally, we need to use a semicolon to finish our line of code. And to evaluate this, we'll press Control Enter. Now, apparently nothing really happened. If you take a look at the geometry spreadsheet, you will notice that now every single point has a density attribute with a value of 0. So what I'm going to do is define this value with a number. So it can be an arbitrary number. What I'm going to use is a value of 1 for every single point. So now let's type density equals 1 and press Control Enter. So we're using the equal sign followed by the value that we want to assign. So it could be 10 or 0.5, whatever you need. So in this case, let's just go with 1. And now we need a velocity attribute. So for that velocity attribute, we can create a single vector value, or in this case, the easiest way to do this is adding a point velocity node. This is a very handy node that will create several vectors. So let me connect this, call this set v, because the name of the attribute is v. I will also change the color of the node. This way it makes it obvious that we have an important value here that we can change. So here on the basic tab, notice how we have an initialization parameter, and the default is compute from deformation. So this means that the node will try to attempt to analyze the motion of whatever geometry we have in this stream and calculate its velocity. But in this case, these points are static, so we need to define a vector rather than calculating their motion. So let's change this value to set to value. And here we have a vector. Of course, the velocity is a vector. And we can define the direction and the magnitude of this vector. In this case, I will push the fluid downward using the y direction. So, of course, if we use a negative value, say -5, we're creating a velocity vector that will push the volume downwards. So let me go back to the scene view, and let me push back a little bit here in the viewport. And what I will do is create a visualizer so we can take a look at this vector that we're creating. So I will scroll down in this toolbar and look for the visualization button. So you can right click on this button, and here under the scene, click on the plus button to add a visualizer. Click on marker, and now we need to define what is the attribute that we want to visualize. In this case, we need a name, a label, and the actual name of the attribute, which is v. Now, the style of visualization, we need a vector, and the color can be anything you want. In this case, the default of yellow is fine. I'll just change the length of the scale to 0.1. And here we can clearly see the direction that we'll have. Try, for example, changing the x value to 5. And this time we'll have a vector in a 45-degree angle going downward and towards the right. Or if you want to push this vector forward or backward, you can use a z value, for example 5 units. This would push the velocity forward in space. Okay, so let's leave this at 0, -5, and 0. And another very cool option that the point velocity node has is that you can add a curl noise, meaning a bit of a randomized vector. So if you click here under the curl noise tab, you will find that by default the add curl noise is turned off. So let's turn this on. Notice how the vectors are being changed. Now this looks a bit random, but overall the vectors are transitioning in a very smooth way. So let's increase the scale to 1.5. If you want the size of these noise patterns to be smaller, you can also change the swirl size. For example, you could bring the value down to 0.75. And also we have a few values, for example, the grain of the noise. So the larger this value is, the more chaotic the noise will be. We can decrease this, for example, to 0.25 or even to 0.2. So a lower grain value would yield a softer transition between these vectors. So let's go with these values for now, and if necessary, we can change them later.